So I think this will be a really interesting talk this morning, and I really thank you, Harrie, for having dedicated time to our course.
Yeah, thank you. Yeah, my pleasure, of course. So what I've done for today is I've picked this introductory presentation into the subject, and I've based it on a tutorial that we created a couple of years ago for the web conference. That's something I did together with Rolf Jagerman, who's now a software engineer at Google, and Professor Maarten de Rijke, who is from the University of Amsterdam. When we created this, we were all at the University of Amsterdam, by the way. All right. So I'll start on a very, very high level, but with, going back to the beginning with search. So I actually was in Padua, I think it was 6 years ago for ECIR. And I remember this really nice basilica that was next to my hotel. Now, of course, you know how a search engine works, right? When you type in the search engine, it has seen millions of results, and now it's decided to show the ones that you see here on screen. What I'm going to focus on today is the ranking, so the system that decides for each of these, in this case, web pages, where it's going to be displayed and what position. And my point is basically that a ranking system that does this web search that you've probably seen a lot in this course is very similar to, it's actually almost identical to a ranking system for recommendation. So this is the video of our tutorial on YouTube. But when you look at that on the side here, of course, you see these recommendations. I'm sure you're all familiar with how this works, right? My point is basically that behind the system that puts these recommendations here is also a ranking system. It's also a system that tries to order these items in terms of how likely users are to want to see them or to click on them. So, of course, there are many other places that we can go, right? We could go to e-commerce, where we rank products, news websites where we rank news, you name it, right? Any sort of search or recommendation usually has some ranking system behind them. So it's very important that these ranking systems work well, because they can really affect the experience that a user has, right? They can really make the difference between how many products are being sold, how many videos are being watched, how many web pages are being visited, etc. To get these to work, we usually optimize the ranking systems with what's called learning to rank. You might have already seen this in the course. I don't know, of course. But learning to rank is a part of machine learning, where specifically we're trying to construct a model that, given a lot of training data, where we have examples of where we know sort of the ordering or the degrees of relevance, that we can sort new objects. So we can apply this model to new objects that we haven't seen before and then rank them as well. Or you might say sort them. Based on their features, of course. Yeah. Or usually based on the features. And yeah, this is really a core task in information retrieval. Like I said, for search and recommendation, this is really important to get it to work. All right. We're going to do, of course, learn to rank from user interactions, which I presume you haven't seen before. But before that, I want to introduce some notation so that we're all on the same page. So I'm going to call R here a ranking. So that's just an ordered list of items. We're going to call them documents, because we're in the information retrieval course, and usually the items are documents, of course. And the ranker is going to be some function where theta are the parameters. So these are, for instance, the model weights or the specific parameters of the model that we want to learn. And then, so the ranking is just an ordering of documents, where R1 is the first in the ranking and so forth. And we're going to sort them on the scores that are given by this model in descending order. So if we give a document to this model, it's going to give a score. We're going to sort in the descending order. We could do ascending. There's really no difference. But for this presentation, we're just going to choose descending. And of course, every document has to be in the ranking, right? We don't want to skip documents. We want to sort everything that we have. The goal now that we have is to find these parameters, find the theta parameters of our model, so that when we sort according to the scores of the model, we get the most optimal rankings. Now, of course, what's the most optimal is ambiguous, but we're going to follow well-known ranking metrics, because that's just the standard way of doing it. So you've probably seen these metrics. I think we'll talk about them later, like precision or DCG. I'm not saying that these are, the best ways to evaluate, but they're very standard. So we're just going to, for this discussion, assume that they do the job that we need them to do. All right. So far, it's probably very similar to what you've seen in the course, perhaps, but there are some caveats, or you might say limitations to this approach. And the ones that I'll be focusing on are the ones that come from the data set. So the way that we do, let's say, supervised learning to rank, so the traditional way, you might say, is through these annotated data sets. So we have a lot of combinations of queries and documents, query document pairs, and there's been human judges who've annotated for them whether the match between the query and the document is good or not. So whether this is a document that's relevant for the query or not. And then given that, you can get a lot of examples, and then you can train your learning to rank model. I'm not saying this is the worst approach. I think it has a lot of advantages. I don't think it's ever going to go away completely. I think it has a good place in information retrieval, of course. But over time, it has become apparent that there are many limitations to this approach. So the idea of getting these annotations from judges and then creating a data set brings several limitations. The most important one, the most obvious one perhaps, is that it's expensive in terms of money, but also in terms of time. You don't just have to pay people to give you these annotations. You usually have to educate them first on how to do that. And so just the investment in creating an expert that can do this is already very costly. So both in terms of time and money, this is a big problem. Of course, there are always these big companies that have a lot of time and have a lot of money, but there are other cases that you can't get around, right? So it can be very unethical, especially in privacy-sensitive settings. The most obvious example here is, I think, email search. So nowadays, if your emails are served on the cloud, you can search through your emails. There's a ranking model that decides what to show to you. But if we had to make a annotated data set here, we would need experts to look at a sample of all the emails. And obviously, we don't want other people to look at other people's emails like that. The same goes for maybe documents that you have in sort of an online office environment or Drive, you name it. But it can be very ethical to have these experts actually look at the documents, usually due to privacy. So it's kind of a non-starter to create a data set here. It can also be impossible for problems where an expert can't really know what's relevant. And this is especially a problem for personalization. So a lot in recommendation, especially, we want to cater to the specific preference of a user, but the only ones who knows these specific preferences are the users themselves. So we can't really get an expert to tell you whether someone is going to like something or not. The same way other people don't know your exact preferences in certain cases. It also turns out that what's relevant changes a lot. So, but the data set is not going to change by itself, right? So it could be that something happens in the world, and now the labels are kind of incorrect. Now a query is probably going to present something else. So you would either have to update your data set, which makes it even more expensive, or the data set will be out of sync. And then lastly, and I think most importantly, is research has found that there's not necessarily an alignment between the true user preferences and the annotators. So when we look at actual user behavior and we look at what the experts think that users are going to do, very often user preferences are slightly or significantly different from what the experts think. That means that even if we have the largest data set that we can find, if we have a really train well, really get the highest performance that we can get, there might still be this the mismatch between what our model ranks and what the users actually want to see. So that means that there's sort of together this shows that it's really hard to get a data set, that there are problems with it, but also that in some cases it might be impossible to get the perfect data set there. So again, I don't want to say that I want to emphasize that data sets are very valuable, right? I think they have a very important place in research and development. I'm not arguing that we should get rid of them. That's not my point. However, this supervised approach to learning to rank is unavailable for practitioners that don't have the budget. If you're a small site that has a search or recommendation engine, you can't afford it. It's impossible for certain ranking problems. So even the largest search engine you can think of can't apply this approach everywhere due to, for instance, privacy reasons or personalization issues. And they're often misaligned with the true user preferences. So if we're going to really focus on the annotated data sets, we're probably overfitting and not relearning the true user preferences in the real world. So for these reasons, there's sort of a need for an alternative way to do things, a different way to optimize the ranking model that avoids these problems. And as you know, probably guess from the title of this talk, it's going to be about learning from user interactions. All right. At first glance, it seems that this solves all our problems, right? If you have some users, user interactions are virtually free. I mean, you have to pay for some storage to store them. You have to do some work to gather them, but you're probably already doing that anyway if you have a significant user base. And user behavior is indicative of their preferences, right? People are going to behave in ways that display what they want to see. That seems a good start, right? That seems to solve the problems that we've just laid out. However, they also come with their own difficulties. And this is mainly because interactions are usually a form of implicit feedback. And what we mean by that is that, well, first of all, there's a lot of noise, right? So users click for many different reasons, and very often for reasons that we don't understand, right? Like, not every click is not a clear signal of relevancy. People can click because, nothing on the screen looks like what they're looking for, but they want something. People can click out of curiosity, even if it's not what they're looking for. People's fingers can slip and they can click. There's many reasons why a click might be incorrect. The bigger issue is actually that clicks often don't happen even though there's something relevant on screen. So clicks may be missing because users may not notice, etc. But this is not a problem if it happens in a noisy way. So in a random way that is not systematic. Because if you have noise in your data, if you just have a large amount of data and you average, the effect of noise is going to disappear. The problem really happens when we have a form of bias. And the reason that's a problem is because bias is a systematic form of noise, you might say, something that you can't average away. I think another way of thinking about bias is that there are many factors that are not just relevancy or preference that are going to affect how people are going to behave, where they're going to click, how they're going to interact, that are also affecting the interactions that we have to sort of disentangle. So give it some examples. The one that we're focusing on today, I think the biggest issue with rankings is position bias. So it turns out that higher ranked documents get more attention. So if a document is placed at the top of the ranking, at the top of the page, a lot more people are going to look at it, are going to consider it, think about clicking on it. And it's going to give it a lot more clicks than something at the bottom of the page, even though that doesn't necessarily say anything about their relevance, right? Another one is what I call item selection bias. So if you don't show a document on screen, users are never going to click on it anyway. So by making the selection of what's showing to the user, that's also going to affect what you're going to see. If you don't take that into consideration, and then then it's some documents are not going to get any clicks just because you haven't shown them, right? If you don't take that into consideration, you might be learning the wrong patterns. And there are many other forms. So presentation bias is also one, especially in more of a recommendation setting. I usually think of, I think it's, for instance, the Netflix homepage where one movie or series get this really big banner on top of the screen and others get these tiny pictures, tiny thumbnails. Obviously, by having so much space and having a nice trailer, people are going to behave differently with that item than with the other ones. And that advantage might be unfair because it doesn't necessarily have to do with whether they really like the item or not. Right. So we have noise and bias. We're not that worried about noise because if you have a lot of data, usually the effect of noise disappears. However, this is not the case for bias. That's one of the key things that we're going to see. All right. Here's a very famous picture. This is the golden triangle. So this is, I think about, it must be 17 years ago when this was made, I think. An eye tracking study where they let users look for a digital camera. And then the colors here on screen show you how many people have looked at a certain place on the ranking. And this red blob up here shows us a place where practically 100% of people looked. So everyone has looked at the top two results, right? They may not have read the entire link, but they've seen the first two results. If we look at this bluish color down here, that's less than 50%. I can't say exactly how much, but less than half of the people that saw this page looked at this result. This is, I think, result number 8. So I don't know what these web pages are, how good they are, but beforehand, we could already predict based on just where people have been looking that there's going to be more clicks up here than down here. Just because we know that half of the people aren't going to make it that far. So half of the people are not going to click here because they're not even going to look, right? They're not going to click somewhere where they don't look. So a result at number 8 starts at a huge disadvantage. It already starts with half of the people not clicking just because of its position. And this is really going to affect the click-through rates that we're going to see. So this is, in a nutshell, where position bias comes from. And it makes sense, right? Because usually the best results are on top, or we don't want to look at everything, right? That's the whole point of the search engine. But if we're going to look at just click-through rates, if we're just going to follow click-through rates to decide which document is the best document, then we can already predict that we're probably going to underestimate the relevance of the items down here and overestimate the relevance of the items up there, right? Just because of this position bias effect. All right. So the goal of what we call unbiased learning to rank is, again, we want to optimize a ranking model based on the relevance preferences of users. So the way that users, the order in which users want to see documents, based on their interactions. With interactions, in this case, I just mean clicks. And what we can already tell is that the only way to do this is to avoid being biased by these other factors, like position bias. If we can already tell now that if we're going to ignore them, then we're going to have a problem. So that's where the unbiased part comes from. That's why we want to avoid being biased here. All right. That's the introduction to the problem. Let's actually get into the meat of it. So there are different solutions. I think currently the field is decided that counterfactual methods are the best way of dealing with it. So that's what I'll talk about today. And the way that we'll do it is we'll start by talking about evaluation. So how can we know that a model is good or not? And actually, the learning follows very easily from evaluation. If we can do evaluation, the learning part is quite straightforward. All right. Evaluation is, of course, very important on its own. The problem here is we have a ranking system or a new ranking model, and we want to know whether it's good or not before deploying it, right? We kind of want to know before we show it to any users whether it's good or not, because if it turns out to be bad and we showed it to users, we might have degraded their experience. So the task in counterfactual evaluation is, can we evaluate a ranking model or function using historical interaction data, so data that we got in the past, from a different ranking model that we're going to call, in this case, fdeploy. So I have clicks based on this model. Can I use those clicks to say something about a new model? It's called counterfactual because this was the model that was in production, but we want to sort of know the metrics as if this model was in production. All right. All right, so don't be intimidated by the math. It's actually very straightforward. I'll walk you through it. So I'm going to use Y here as the relevance labels. And they're going to be binary. So if we most IR metrics are linearly decomposable in a way like this, where this is going to be our metric for our ranking model, our document set, and our relevances. And for each document, we're going to give it a weight according to its current rank, and then multiply that with its relevance. And then just do this for each document and then sum it. And this already gives us many of the standard ranking metrics. For instance, average relevant position is just where the weight here is the rank itself. So this is something you want to minimize. If there's only one relevant document, this is the mean reciprocal rank. DCG, which you've probably seen here, the weight is going to be 1 divided by log 2, the DCG weight, right? And for position, the weight here is just going to be a 1 or a 0, indicating whether we're in the top K or not. And then, of course, we have to divide by K, but you can think of it just as a binary variable. So my point here is just, for all these metrics, we can express them in this formula here. By working this way, by working with the formula this way, we're kind of saying we're solving the problem for all these metrics at once. And you can choose the metric that you like, of course, when you're actually applying it. In the full information setting, this is very easy. It's probably been an assignment in your course. Let's say here I have a scenario with 5 documents, where document 1 and document 4 are relevant. If I asked you to calculate DCG or precision, this would be very easy, right? There would be, you just could do it on a piece of paper. You may have to do it for your exam. So that's, I don't have any information about your exam, but my guess would be that this is usually an assignment that you might see.
You see, it's the same all over for the exams.
Exactly. However, when it's not your exam, when you're actually working with real users, with their clicks, you don't observe the actual labels. You don't see the actual relevance labels, you observe the clicks. And as we talked about, clicks are biased and noisy indicators of relevance. In particular, I think the important part is that a missing click doesn't mean something is not relevant. So if we go to the scenario again, let's say we have a user that starts browsing at the top and then sees this document, sees that it's a good match, decides to click on it. Keeps looking, says, that's not really a good match, doesn't click, sees the third document, thinks, okay, maybe this is, it's in number 3, it's in the top 3. He's looking for more information, this might be good. because it's in the top 3, even though it doesn't look good, clicks on it anyway, finds out it's not what it's looking for and stops looking, right? So it's never looked at document 4, never looked at document 5. So the way that we can interpret sort of this position bias, this examination behavior, is kind of as a filter, right? So we have the true relevances, but not all of these relevances make it to the other side. And some of them actually flip, like irrelevant documents may still get a positive signal in terms of clicks. So this is what we're dealing with. All right. So there are many reasons why a click may not occur, as we talked about, right? It may not be relevant. That's sort of what we would like to find out. User may not have examined it. And then there's all these other random reasons, right? And as I said before, if these reasons are, some of these reasons are noise, and then we don't care about it that much because you can average noise away if you have a lot of clicks. But there's also a bias, and here averaging is not going to work. So that's the important difference, and that's what we're going to consider now, right? So I'm going to introduce an examination model. So where this is a very basic user model, so it's a probabilistic model of how users might behave, and the probability of a model being examined, where O indicates whether something is examined or not, is going to be the probability that O is 1 for a certain document. So this is the probability that a user is going to take a look at a document, basically. And it depends where it's placed in the ranking, right? So it's conditioned on both the ranking and the document. The probability of a click, so someone's going to click on a document, it's going to be conditioned on whether it was examined and whether it was relevant. So the idea is that a click is just based on a decision that a user examines something and then considers whether it's relevant or not. And importantly, clicks only occur on examined documents. So the probability of a click is really the probability of a click given that it's examined and that it's relevant, multiplied by the probability of it being examined. So another way to think about it is first you have the probability, is a user going to look at something? Are they going to examine it? If that's the case, if you get the positive outcome there, then it's the probability of, is it actually relevant? So there's these two steps, right? Okay. It's a very basic model. I'm not saying that users really behave this way. Every model is always incorrect, but it's very useful. And using this model already gives a lot of insight in what happens with position bias. So I'm not saying that this is an extremely accurate way of the way people click on things. It's just like the most basic model where you can put position bias in there. And then later work has introduced more complicated models. But already with this model, we can see the problems with position bias. So let's say that I haven't convinced you to consider position bias, and you're just going to naively follow the click-through rates. So a naive estimate of a ranking metric could be the following. For each document, you have the weight per rank, right? So remember, this would be like a 1 or a 0 for position, or a DCG weight based on where you want to place a document. So where the new model is going to place a document times whether the document was clicked or not. So I've just taken the relevant signal and I put the click signal in here. Then what we're going to do is we're going to apply this to many clicks and then take the average result, right? So, but for each of those clicks, we're just going to treat the click signal as a relevant signal. What we can do now, because we have a model of click behavior, is we can calculate an expectation. So I'm just going to ignore noise for now to make things easier. I'm just going to say the click probability is just going to be the label, so a binary label, right? So if someone sees something relevant, they're always going to click. If they examine something non-relevant, they're never going to click. So we're just ignoring sort of the noise for now. But what we can do then is we can take the expectation. In this case, the examination is the only random variable. And we can, we just put this formula in here. And what's going to happen is instead of this click here, we're going to have the probability of observance, and then for each relevant document. So basically what we're saying is, instead of the click, we're going to have the probability of observance and the relevance here. Now, the problem here is that this is not the metric that we want, right? Like the metric we wanted was the one where this is just relevance. For each relevant document, we just want to have the weight. But we now added this observance probability in here. And we've done this, we have this in the expectation. So it's not something that disappears if you take more and more data, because it's the expected value, right? So this is where we're going to converge if we get a lot of data. And so another way to think about this is that if we ignore position bias, we're actually weighting documents according to their observation probabilities. So our metric is going to add this weight here, which has nothing to do with relevance, just with how we displayed the document when we were logging data. In rankings, as you saw from the eye tracking studies, right? Documents at higher ranks are more likely to be examined. This is what we call position bias. So if we think it for a second, what this means, right? What this means sort of in practical terms when we do evaluation, it's a form of what we call logging policy confirming behavior. So if a document is displayed higher when we were logging data, right? So if when we were gathering clicks, we show something at the top of the ranking, it's going to be more likely that it's incorrectly considered as more relevant. So the documents that are already on top of the ranking have this unfair advantage, and it's likely to keep being enforced. So something gets clicked because it's on top of the ranking. Then when we're learning from the clicks, we're going to put it at the top of the ranking again, which gives it more clicks again. And we're never going to get out of this loop, basically. The solution here, the solution that's most common, has been inverse propensity scoring. This is a method from counterfactual learning in general. But the idea here is that we're going to weight clicks depending on their observation probability. So some of these clicks get overrepresented when you compare it to relevance, and others get underrepresented. But we can actually weight them in a way to account for that. So the main idea is, if you're in the top of a ranking list, when we're logging, right, when we're gathering clicks, you have a high observation probability. So we give you a smaller weight, so that we're saying, well, these are, they have an advantage, so we're going to sort of make them less important because they're overrepresented. Clicks at the bottom of a ranking list, we're going to give a large weight. We're going to say, well, these are underrepresented, so we're going to give them more weight to account for that. So very straightforward idea. And then if we want to do that mathematically correct, we're actually going to, that leads us to the following estimator. So same thing, right? We're estimating for a ranking model, for a document collection, for a set of clicks. And what we're going to do is, for each document, we have our weight. So this is the weight based on the new ranking model, right? The DCG weight maybe, or the precision weight for the new ranking model. And we're going to divide that by the examination probability. So this means that the lower the examination probability, the higher this value becomes, right? Because if you divide by something less than 1, it's going to go up, and the other way around. So the higher the observation probability, the smaller this weight is going to be. But remember that the bottom here is determined by logging. So the ranking that we showed when we were logging clicks, while the top part is determined by our new model. So it's sort of the difference between how clicks were logged and how a document is going to be displayed in the new model. Again, this works for any metric that follows the formula that I stated earlier. Now, it's very easy to show that this is unbiased. We're doing the exact same thing as before. We're basically replacing a click here with the click probability. And what that looks like is we're replacing the click here with the probability of observation and the relevance. So we're doing that down here in the summation. I wish we had done it to the right. It's a bit more clear. But we're saying basically summing over all the documents where the observation is 1 and the relevance is 1. The probability of the observation being 1 is just, the probability of observation. So it's the same steps as we took before, but now because we were already dividing by this probability, this is going to cancel out. So we're actually left with the original evaluation metric in expectation. So to put it in other words, because we know that this click probability is a combination of probability of observance and relevance in our model, like our very simple click model, we're preemptively dividing the probability of observation away. And this is going to automatically weight a click more or less, depending on this, how likely it is to be observed. Now, in expectation, this works, as you can see. So this basically means that we're going to converge on the right value. I've ignored click noise here. It still works. If you add click noise, I'm not going to go to the proof, but we can show that the relative difference is still the same. So maybe you don't get the exact metric value, but you still have the point that the higher the estimated value is, the higher the actual metric is. So you can still say, like, this model is better than that model, which is all you need for optimization. But noise doesn't makes it hard to get the exact value because there's going to be more clicks than relevant items. But that's okay. I'm not going to explain that here, but so I'll just hand wave that away, just so you know this is something that's been accounted for. All right. Do people want to ask questions in the middle, by the way, or what's the usual way that you do things?
Yeah. Any questions, guys? Everything clear so far?
I have a question.
Yeah, go ahead.
I don't understand the relevance depend only on the document, but it should depend also on the topic or where you're at.
Okay, so the question is the relevance depending only on the document or also on the topic? I mean, in the questions, it's not apparent the topic part, I guess.
Right. So we're kind of agnostic to that. So we don't. Our assumption is that a click is a combination of probability of observance and relevance. I'm trying to see if I have the formula here. So the idea is basically that what we call relevance is just how likely people are going to click on the item, given that they've looked at it. So this is not a great definition of relevance because it ignores something like clickbait. You can take extra steps to deal with that. We're just keeping it simple for now. Usually sort of that relevance is unique for both the query and the document, right? So if we change the query, then the features are going to change. And so for the ranking model, it's also going to be a different case. I think that's that answers your question, right? So it's not that we have the relevance, one relevance for all documents and all queries. It's like per query per document we have a different number here. I've ignored the different queries. So everything I've talked to so far, I've acted as if there's only one query. But the same applies if you do it to two different queries. Like you would just take the average over them.
Okay, thank you.
Any other questions?
At the same time, do you usually take a break in the middle, or?
No, we do the 90 minutes stage because for COVID it's 2 hours, but we have to
Okay.
half an hour between one lecture and the other.
Sure, sure, no problem. Then I'll just keep going. All right. Okay, so we talked about evaluation so far, and I've shown you sort of intuitively what position bias looks like, but also in sort of formal mathematics, how you can look at it with by calculating the expectation, you can see whether something is biased or not in a statistical sense, and why that's a problem. And we've seen that in our very basic model of position bias clicks, we can use inverse propensity scoring to correct for it. Now I'll say a little bit of how we're actually going to do the learning after we have the evaluation. So the main problems that we run into, if you want to use this to optimize the ranking system, are actually the main issue that we run into when we're optimizing ranking metrics, right? This is not differentiable. Because of this rank function here, there's not a smooth way that you can optimize the ranking function. As you probably may have already seen, it's when you change the a ranking model, the ordering suddenly changes, right? Like suddenly you have a different ordering, and that it's very hard to learn, right? We kind of want our loss space to be smooth so that we can actually gradually improve over it instead of having these sudden changes. So how do we deal with that? And there are many ways, but usually the way is to have a bound on the metric. So you might have seen methods like lambda rank or lambda mart. And the trick there, what they're actually doing behind the scenes is they're taking a value that's always smaller than what they want to optimize and optimizing that. And so basically, we want to optimize this, but we don't know how to do that, but we have this other value that's lower, and we're going to push that up, and then hopefully it's going to push the other thing up as well. So by optimizing a lower bound might do that. I'm not going to go into detail how we get that lower bound here. I don't think it's good for sort of the scope of today. But the general overview is putting it all together, right? We have to start with a model of position bias. I'll say a bit more about how to do that later. Get a very large click log. So get click logs. If you have a search engine, you probably have them lying around somewhere. For each click in the click log, you have to compute the propensity or estimate it. You have to estimate like how likely was this item to be observed or not. And then based on these propensities, you can calculate a gradient on the bound of the unbiased estimator. So this is the weight of the current model. So for instance, the current model where it places this document in a ranking. But then instead of the actual rank function, you could use something that approximates the ranking function, but is differentiable and preferably is like bounding it in the right direction. And but before you take the gradient, you divide it by the propensity. So this gives it that weight. So the documents that are less likely to be examined will have a much larger weight than the others. And then you can update your model by adding or subtracting the gradient depending on what direction you're going. And you can repeat this process indefinitely. So this is very similar to standard learning to rank, except that we're now, having this model of position bias, having these propensities, and using them to add weights during the optimization process. I want to give you an idea of what that looks like. However, we don't, at the university, we don't have an actual search engine. So what we usually do is we simulate these experiments in a semi-synthetic setup. So we use data sets that are from real search engines. So there's one from Bing, there's one from Yahoo that's very famous, for instance. I'll show you the results on Yahoo today. So these are real data sets that have been used to optimize the Yahoo search engine. And then we generate clicks on them based on a sort of a baseline ranking model where these clicks have position bias. And this gives us an insight in what happens, right? So that looks like this. On the x-axis, we have the number of training clicks. This is on a logarithmic scale, right? So we're going from 1,000 to 100 million. This is the average relevant position. The lower, the better. So we want them to be as low as possible. This is the production model. So this is the model that we use to simulate clicks. It's quite good. But the Oracle model down here, so this is the model if we know all of the relevance labels, right? Which in practice we wouldn't have. But in a simulation, we can actually look at that. So we know this would be the best performance that we could get. And then this blue line here is if we were to ignore position bias and just train on the clicks as we see them. And the key here is that we see that we're converging after 100,000 clicks. And then when you go from 100,000 to 100 million, so 1,000 times more data, we don't improve performance. This is a clear sign of bias, right? So having 1,000 times more data, but not improving while we're not at optimal performance, that means we're optimizing something else. We're converging on the wrong place. If you're not in a simulation, you don't know where this line is, right? You don't know where optimal performance is. So you would never know. Like no one's going to tell you like, hey, you're converging on the wrong place. If you ignore, so if you're just working with clicks, it's very hard to know whether you're in this position or not. And then finally, we have this cyan line here. This is the inverse propensity scored estimator. And it actually reaches optimal performance. It gets rid of the position bias, but it has a lot of variance at low numbers of clicks. So this is the bias variance trade-off. So like the amount of clicks that you need to improve over the naive approach isn't that large, but still you need a lot of clicks, right? So there is some risk involved with inverse propensity scoring, but there are also ways of dealing with it. I'm not going to talk about that here, but usually what people do, they do something in between. So when there's a low number of clicks, we might say, okay, we're going to apply something that's closer to the naive model. And as we get more clicks, we're going to go closer to the IPS model so that we have the best of both worlds. All right. Now, there's one part that I've ignored so far, which is how do we get these propensities? How do we actually get the position bias that we need? What we've seen so far is how to perform counterfactual evaluation. So how do we evaluate? And then how do we learn? I've talked about that. But for both of these, we really were depending on these propensities. And without them, we can't do much. So we need a way to get them. Luckily, there are several ways. The key assumption we're going to make here, which is again an assumption, is that the observation probability only depends on the rank. So all you need to know is the position at which an item is placed, and that gives you the probability of how likely it is to be examined. Again, this is a simplification, but it actually works quite well in practice if you make this assumption. So For each position, we have this number, and we need to know it. We need to estimate it. Now, the easiest way is just pure randomization. So if you have, let's say, 4 documents, we can show them in the order 1, 2, 3, 4. But we could also show them in the order 3, 4, 1, 2. Or this is 2, 1, 4, 3, etc. So we could show them in a completely random shuffled order. So each time the query is being issued, we can randomly decide the order. And then for these 4 documents, the likelihood or the probability that they appear in a rank, all these ranks, is the same. So that basically means, in expectation, if we do this many times, the difference between these ranks is not going to be in relevance, because they're going to show the same documents over time, right? Like if they're equally likely to show each document. If you repeat that many times, the difference is not going to be which documents they've shown. It's just going to be where the rank. So if you just shuffle your documents and you look at how many times do people click on rank 1 or 2 or 3 or 4, you'll actually see these differences. So I know companies who did this, and you can see quite big differences, which have nothing to do with the documents that were being shown, because again, they're the same distribution, each rank. They're just about the position bias that people have. So this is a very easy and very effective way of finding out what these propensities are. You probably can already see why this isn't a very popular approach, especially for companies that already have a good ranking system. Like if you already have a good search or recommendation system. And that's of course because, you know, we're now showing randomized ordering. We talked about how the ordering is important, and here we're basically messing around with the users, you might say. We're messing with the user experience just to get these propensities. So it's not a very popular approach, but it works. It's the most basic approach. I've seen people use it, especially when they have a new product and they don't trust the ranking system anyway. Then this is a good way to just get your, in recommendation settings, this might also not be so bad because the users don't realize that you're doing it. In search, it's usually not a good idea because people will notice that, you know, the ordering doesn't make sense. So it's very effective, but we would like something that's a bit more respectful of the user experience. So the trick here is basically that we still want to do randomization, but we're going to do it less severe. So one of them is a rand pair, where you pick 2 documents and you swap the 2 ranks and you swap them. So you could, for instance, swap the first document and the second document, then the second document and the third document, then the third and the fourth. So you're never swapping more than 2 documents. But if you do it for all these positions, you can work out what the propensities are. A nicer way is interventional sets. So I think I'll talk about that. Yes, yeah. So I don't know if you've heard of A/B tests in your course already.
No,
or you...
just mentioned.
Okay, so very often in all online products, what they do is an A/B test. It's a way to find out if, let's say, ranker A is better than ranker B. For instance, you can show 50% of the users. So randomly, if you pick 50% of the users, you show them system A, the other half you show them system B. And then afterwards, you can look at, okay, where did I see, what change did I see in user behavior? Is this better? Is this worse? This is extremely common. So whenever you open a search engine, you're probably part of at least one A/B test, maybe 2, 3, 5, like it's going on all the time. Maybe not always with the rankers, but A/B tests are like in every product that you're using continuously. The data that's being collected here is actually also a form of randomization. So in this scenario, because ranker A and ranker B disagree about the placement of two documents, it's actually as if we're swapping those two. And if there's more A/B tests at the same time, you might be in a situation where you have multiple forms of randomization at the same time. The end result is that you again have data where you can work out the difference between the positions, right? So for document 2, you can look at the click-through rate when it's displayed in the second position, in the first position, and then if you have enough data, that's going to give you an accurate estimate of the difference in propensity. This is very similar to randomization, except it's not so severe. And a lot of companies are doing A/B tests anyway, so they have the data lying around. So they're very happy with this approach, and that's why it's very common right now. Okay. Then lastly, there's also learning the propensities and doing the unbiased learning at the same time. These are, depending on the approach, popular. So the idea is basically that if you know the relevance probability and the click probability, it's really easy to work out the observation probability. But if you know the observation probability, you know the click probability, you can work out the relevance probability. That's what we've done so far. So some people have suggested that you can get the relevance by. So what we see up here is what we've done with so far with counterfactual evaluation. But you can also actually swap this part down here and put that over there, and then you get the propensity. So the idea is basically that, okay, you learn a relevance model, and then based on the relevance model, you learn the observation model, and then based on the observation model, you can update your relevance model to be better, and then you keep repeating that process, and then hopefully they converge on a good estimate. With expectation maximization, for instance, that works quite well. So that's another way, if you don't have any randomization, but a very diverse data sets, many different documents, that might still work quite well. All right, I'm going to end with some practical considerations. So one of the problems that I've shown you with this approach is that it has a very high variance. Variance can come from many things, right? Like if we don't have a lot of data, we get variance. In our scenario, it's when you have extreme position bias and these propensities become very small, the weights become really large. And what happens is that only a very few clicks determine overall what the loss or the evaluation is going to be, because they have the largest weights. And this could explain why with low data, we saw really bad performance of IPS. And a common solution here is just to do clipping. So when you do the IPS, instead of dividing by the propensity, we divide by the maximum of some value, some parameter, and the actual probability. This adds some bias, right? Because we're no longer dividing it away perfectly. But when the value is very small, we prevent this weight from getting too large. If you set this weight to 1, you have the naive estimator again, by the way. So to go back to the figure we saw before, if we add clipping here, we get this. This is dynamic clipping, so the clipping weight is being made smaller as we get more data. And you can see that we can actually find sort of almost the perfect trade-off between the naive version that is good, that has low variance, but biased convergence, and the IPS model that has high initial variance, but has really good convergence. So that's the purple line we see over here. All right. Okay, let me wrap up because I think we're almost out of time. Compared to supervised learning to rank, where we use manually annotated labels, I've talked today about counterfactual learning to rank, where we use click logs. In supervised learning to rank, the problems are mainly of using this data set, of the data sets that we need, which are expensive, very often impossible to get, and they're very often not aligned with the real user preferences. An upside, though, is that the optimization is very well studied. So it's very well known, like we know a lot what's going on there. but it's very often not available for practitioners. In comparison, counterfactual learning track, we use click logs, which are very cheap. They're very easy to get, but they're noisy and biased. That noise is not a big problem. We can get rid of that by just averaging over a lot of data, but those biases don't disappear from gathering more data. So we actually have to mitigate them in some way. Today, I've talked about inverse propensity scoring. There are more biases than just position bias. There are more complicated models. There are some other techniques, but what we've seen today is the basis. So this is sort of where it all starts. By solving the problem of the annotated labels, by using clicks, we have our own problems to solve, and you've seen one solution for that today. What I hope that you take away from today's lecture is user interactions with the rankings are very biased. So when you're working with clicks on rankings, bear in mind that there's a lot of factors going into them. There are not just whether someone likes something or not, especially the way that you log the data is going to affect the data that you observe. Counterfactual learning to rank tries to correct for that. We've talked about that with inverse propensity scoring. You need to make assumptions about how users interact, though. But if you have them, you can have these corrections, and then you can have your unbiased learning from historical interaction logs. All right, it's a very active field, so there's a lot of recent work that you could look at, of course. And yeah, thank you for your attention.
Thank you very much, Harrie. So, any questions, guys? I have a question. Ifenardelli, you had a question? Alessio?
Yeah, yes.
Go ahead first.
Okay, I'll make an example. So the usual way a user interacts with a search engines is to type a query and find document, and if he is not satisfied, he retype another query. Is it possible to account for this in learning to rank?
Yes, yeah. I think as long as you can, if you can have a model, so you need to make assumptions about the user behavior. You would be able to deal with that, yes. So it might be that when we see someone retypes the query without clicking or without clicking and looking at a page for too long, that could be a signal that we didn't show the right items. So there could be a bias there, right? It could be that we were showing the wrong items, and that affects the data that we've seen. So you would want to correct for that. You would want to maybe take that as a negative signal to say, like, okay, this user really didn't like what he saw, so because he went to a different query. We could try and say, oh, for the second query, the documents that were found there should have come up in the first query, and try to use that. I think the danger is that if we do this, if our assumptions are wrong, if the user retyped the query not because they didn't like the results, but because they just had another thing to look for, like a different topic that had nothing to do with the first, that we might be learning the wrong thing. But the basic principles of like noise and bias would still apply. Like we want to still avoid systematic mistakes and still want to work with the noise. Yeah, my answer is a bit generic. I'm sorry about that, but it's hard to work on this because we don't have real users. So I can't. I mean, we could think of a mathematical model and we could solve that, of course. But we need a combination of like, we need to know that the mathematical model actually works quite well in practice. So for what I've shown today, I forgot to mention it, but it's been applied in, I know at Google, they work a lot on it. So in the Chrome Web Store, in Gmail, Google Drive, all apply a version of this. archive. So at Cornell University, if you're looking for papers online, you probably found archive. They're also applying this, and there's more examples in the literature where people have applied this techniques and they found really big gains. So one of the last papers, I think, on the Chrome Web Store found an 11% increase in people clicking on items. So that tells us that, you know, the assumptions we make are probably okay because they lead to real improvements. So it's, yeah. So we would like to have more complicated assumptions, but we rely on people with real systems to verify whether these assumptions actually make sense. All right, so there's a very long question, a long answer to your question. I hope that I've.
Thanks very much.
Sure.
Any other questions, guys? Okay, so you mentioned that you have shown that you need in the order of millions or hundreds of millions of clicks to get a reliable estimate. How computationally heavy is to train and then to use these models? Are they very demanding?
I think they're not. I think the costs is about the same as. I don't think there's much added costs if you're already doing the learning to rank, because it's just about adding these weights. So the additional cost isn't much. But if we talk about the really big tech companies like, say, Google, the way that they're learning a system is not the way that, at least at my university, we would ever be able to do it, of course. So also in terms of the amounts of data, I understand that, you know, the numbers that we're talking about here, millions, are no problem for them. Like that's, I don't know, that's probably a matter of weeks, or I have no idea, but they don't have to wait very long for that. So they're already used to these scales of data. There's more recent work that actually makes the requirements much smaller, so that you don't need millions, but you need hundreds of thousands in a simulation like this. That also helps.
Thank you very much. And are there any libraries that students can use for estimating these models that you have presented, or should they implement it themselves?
I think so. A lot of papers share their code. There's also this thing called TensorFlow Rank, created by actually these people that applied it to Gmail and Drive and Chrome. That has options for adding like propensities to the learning process. So that's a good point to start if you want to apply this in practice.
Thank you very much. Any other questions, guys? Okay, so Harrie, thank you so much for the lecture. It was very inspiring and very, very clear. And thank you for the time you spent with us in the course.
My pleasure. Yeah.
Wish you a nice day.
You too, and good luck with the rest of the course for all the students. All right.
Yeah.
Ciao.
Bye bye.